let's continue. Our next speaker is Professor Ming Chang from Tsinghua University. The title is Q-cohomology problem from black holes. Let's welcome.
Okay, thank you. First, I would like to thank the organizers, especially Professor Yao, for inviting me to speak at here. And so my talk will be based on this series of work with my collaborators. So first, so we all know that the black hole were first discovered as a singular solution in general relativity. And usually people expect that the resolution of the singularity requires quantum mechanics. And the singularity cannot be resolved purely within the classical general relativity framework. And black hole has another very important signature is that the black hole carries a large entropy. And this entropy is proportional to the horizon area and follow from this Beckstein-Hawking formula. The Gn is the Newton's constant. And there's another way to understand entropy is in statistical mechanics. The entropy has a meaning that is the log of the number of microstates. And so the black hole must contain a lot of microstates. And I believe that these microstates cannot be explained within the classical relativity, and that due to the no-Hale theorem. So no-Hale theorem tells us that black hole carry very few degrees of freedom, and these degrees of freedom cannot give us that many microstates. And again, to understand the entropy of black hole, that require quantum mechanics. And the best understood formulation of quantum gravity is in entity zeta space through an exact duality. That's called the ADS-CFT correspondence. So it's a duality between quantum gravity in ADS space and the conformal field theory on the conformal boundary of this ADS. And using this exact duality, the quantum gravity states, including black hole microstates, are due to states or operators in the boundary conformal field theory. And in this talk, I will focus on one of the ADS-CFT dual pair. That is, on the gravity side, we have 2B string theory on ADS5 times S5. And on the CFT side, the dual is the 4D n equals 4 supersymmetric Yang-Mills theory. And so ADS-CFT correspondence is a strong-weak duality. The quantum gravity in the semi-classical region, so that's where the black hole live, are due to a strongly coupled CFT. And that this property gives us some problem of using ADS-CFT to understand black hole because we need to study strongly coupled CFT. But one way out is to introduce supersymmetry. And supersymmetry allows us to probe strongly coupled physics from just perturbative computation at weak coupling. So that's by the fact that many physical observables that preserve supersymmetry are actually independent of the coupling constant. So they do not depend on whether you are at strong coupling or weak coupling. So we can study Rose quantities at weak coupling and then use Rose quantity to understand the strong coupling physics. And such observable usually involve PPS states or operators. That means that involves some state or operator that preserves supersymmetry. And there's another advantage of studying these observable is that they are better, more precisely mathematically defined. And so the PPS state and the operator are defined in the following. So we consider the n equals 2 supersymmetry. That means we have a supercharge Q and its Hermitian conjugate Q dagger. And the anti-commutator between Q and Q dagger give us the Hamiltonian of the system. And both Q and Q dagger are nilpotent, they square to 0. And that's the algebra that we require the theory to have. And the BPS state is defined as the state that is annihilated by the Hamiltonian. And equivalently, these states are annihilated by both Q and Q dagger. And BPS operators are defined in a very similar way. And then we can use the standard Hodge theory argument that tells us there's a one-to-one correspondence between BPS states and the Q-cohomology classes. The Q-cohomology is defined in the very standard way that we consider the Q-closed states, the states that are annihilated by Q, and then mod out the equivalence relation that basically the Q-exact state. If a state is Q acting on some other state, we mod it out. And so this one-to-one correspondence is, the standard correspondence in Hodge theory that if we usually the rule played by the BPS state are the harmonic forms, and the cohomology is the Dirac cohomology. And in that case, we know that there's a one-to-one correspondence. And here we just use a very similar argument. We can get this correspondence. So to study BPS state, we can actually study a easier quantity, that's the Q cohomology. And you can see that the Q cohomology does not depend on Q dagger. It only depends on Q. And that's why it's simpler. So this is outline of my talk. So I would discuss the Q cohomologies in n equals 4 superyamules, and then a black hole actually give us prediction on what on properties of this cohomology, and then I will discuss some generalizations, generalize the Q cohomology problem to other theories, and then conclusion. So let's start with n equals 4 superyamules, and recall that we rely on this duality. On the gravity side, we have 2B string theory on ADS5 times S5, and on the CFD side, we have 4D n equals 4 superyamules. And let's first focus on the gravity side. On this gravity side, it is known that we have supersymmetric black holes in ADS5 times S5, and these black holes preserve 2 supercharges. And these black holes, under this duality, they are due to the minimally supersymmetric states. In other words, there are 116 BPS states in n equals 4 superyamules. And these states are the states I discussed before. They preserve 1 supercharge Q and Q dagger. And these black holes carry 5 angular momentum. And so these 5 angular momenta corresponds to 2 rotations in ADS5 that give us J1, J2, 2 angular momenta, and 3 rotations in S5, Q1, Q2, Q3. And all these angular momenta are proportional to n squared. And the entropy of this black hole also proportional to n squared. Okay. So now let's come to the CFD side. So on the CFD side, we can use the state operator correspondence. So instead of talking about BPS state, we can talk about BPS operators. And in n equals 4 superyamules, we have more than the n equals 2 supersymmetry I discussed. So in n equals 4 superyamules, we have 16 supercharge and 16 conformal supercharges. But for our purpose of studying BPS state, we only need 1 supercharge Q and its Hermitian conjugate. So we just pick 1 Q, and we only need to require like Q squared equals 0, and its Hermitian conjugate is a conformal supercharge, usually called S. And then we have the structure we need, the anti-commutative of Q and Q dagger that give us some bosonic charge that previously I called it Hamiltonian. And in n equals 4 superyamules, it's a linear combination of the dilatation charge and these 5 angular momenta. And then the BPS operator are defined in very similar way. They are the operator with delta equals 0, and they are annihilated by Q and Q dagger. And now let's try to construct some cohomology classes in n equals 4 superyamules. And the way to construct them is let's first basically try to construct the space that Q act. So basically the space of local operators n equals 4 superyamules. And so now so in particular, let's consider the theory with SUN gauge group. So the operators are SUN invariant composites of the fundamental fields and covariant derivatives in n equals 4 superbinomials. And here I give the list of fundamental fields and covariant derivatives. And so we consider SUN gauge groups, so there are n by n matrices, and we have 6 Bolzani fields, 5 ij, there are scalar fields, and some spinors, gauginos, and gauge field and covariant derivatives. So these ij are the SU4 R-symmetry indices, and this mu is the 4D space-time index, and this alpha and alpha dot are the 4D spinor indices. So we have these fundamental fields. So to construct operators, we just need to consider the gauge invariant composite of these fields. But our purpose is to construct some BPS operators or something that can contribute to the Q-cohomology. So we only need to consider the the fundamental fields and covariant derivatives that satisfy the delta equals 0 condition. And so basically we just select out of the previous list of fields, the fields that satisfy this condition. And then the problem is a bit simpler. So we have 3 scalar and some 3 fermion and 2 gaugino and 1 component of the field strength. And also these 2 covariant derivatives. And we can further simplify this problem by assemble these fields into a generating function. And it's actually a generating function involving both Bolzani and Fermiani variables. So we called it a BPS superfield. And the way to assemble them is in this formula very explicitly. So we introduce the Bolzani variable z plus and z minus to take care of the actions of covariant derivatives. So we have this formal sum. And if we expand the function in z, then we get terms with different number of covariant derivatives. And this Fermiani variable or Grassmann variable, theta 1, theta 2, theta 3, are used to assemble different type of these fields. So you can see that they nicely sit into this formula. So because these theta are Grassmann, so we have a finite expansion up to the third order, theta 1, theta 2, theta 3, because theta squared equals 0. And so they sit in this very nice form. And so these fields are, at least generating functions are has no constraint, but it also has one constraint, that is, if we set all z and theta to 0, you can see that this formula vanish. So we have this constraint. So then after imposing this constraint, we can forget about the previous fundamental fields and just work with this generating function. And now we just want to consider the gauge invariant combinations of them. So for example, this is one of the gauge invariant combination. We just take some products of these fields and take traces. And equivalently, that can be rewritten in the generating function language. And another advantage of using this generating function is that this Q acting on this BPS superfield take a very simple form. So Q act on psi just equals psi squared. And also Q satisfies Leibniz rule. And so we have this. And now basically that set up the problem we want to solve. We want to consider the Q close operator, that is the gauge invariant operator of this form, and we want to ask them to be Q close and then mod out the Q exact one. So this Q cohomology is actually nothing but the relative Lie algebra cohomology of this form. And the Lie algebra we have is a GLN, and with this this GLN A is that's the Lie algebra of n by n matrices with entries in this algebra A. So this algebra A basically that's the polynomials of the auxiliary variable I introduced. And you can see that basically the space of the BPS words, they are this gauge invariant operator constructed out of the generated function, are the basically relative cochain, and Q is the differential. And it's relative because we impose a gauge invariant condition, and also the condition that if we set all z and theta equals 0, this generated function equals 0. And so now let me discuss the cohomology classes at infinite n. So the problem actually becomes simpler if we set n to infinity. And if we set n to infinity, we can exactly solve all the cohomology classes. So to present the result, let me introduce some more formal variables. So let me introduce the differential forms of the auxiliary variable z and theta. So this dz will be anti-commuting, and the d theta will be commuting. And then with this, I can define d psi to be basically the exterior derivative of psi. And then our previous Q action becomes Q act on d psi, just give us a commutator of psi and d psi. And now let's just try to write down some formula that will be annihilated by Q. And it's actually quite simple to see that if I consider trace of d psi to the n-th power, and this formula obviously annihilated by Q. And then so we get so using this we get a bunch of single trace operator, and that basically by expanding further expanding this formula, so we get these single traces. And it's also quite easy to see that these things cannot be Q exact. So they are Q close but not Q exact, so they represent some cohomology classes. So if we phrase that in mathematical terms, these single trace cohomology are actually the cyclic cohomology. And basically, the way to view it is to think of the traces as a degree n-1 cyclic cochain. And there is a theorem proved by Zagan, Lode, and Quillin, is that in the infinite n limit, if I consider GL infinity, then the cohomology is actually isomorphic to product of the cyclic cohomology. So this theorem tells us that at infinite n, all the Q cohomology classes are given by product of this form. Okay. So now under ADS-CFT correspondence, let's try to understand what these cohomology classes mean on the gravity side. So these single traces, these cyclic cohomology classes, they are due to single graviton states in ADS5 times S5. And we can verify this expectation by just matching the Betti number of this cyclic cohomology with the number of single graviton states. And we found that they exactly match. So the interpretation of this cyclic cohomology are the gravitons in ADS5 times S5. And now we can consider product of this cyclic cohomology. And then the natural duo of them are the multi-graviton states. So that's because if we, in the n to infinity limit, the G Newton, the gravitational coupling in the bulk goes to 0. So the multi-gravitons are basically product of single gravitons. So now we've understood the infinite n case and also the graviton case. Let's proceed to try to compute and understand the cohomology at finite n. So to consider finite n, there's a very useful way to introduce, to go from infinite n to finite n is to realize that the Hilbert space of operator at finite n can be written as this quotient. So we first consider the space of operators at infinite n. So they are basically the space of multi-traces. And then this IN means the trace identities. So for example, if you consider n equals 2, these multi-traces are not linearly independent. There are some identities involving different number of traces. So IN will be the space of these identities. And if we quotient out by these identities, we get the finite n space of operators. And so this structure can be rewritten as a short exact sequence. And this pi is the quotient map. And now we want to take cohomology of this short exact sequence. And that will give us this long exact sequence. So, and we see that the thing that we previously computed, that's the infinite n cohomology, see that here. And and also from this long exact sequence, we can see that actually some of the finite n cohomology, you can obtain them from the infinite n cohomology by this pi star map. So and also so basically some of the finite n cohomology are live inside the image of this pi star, and then using the exactness of this sequence, that means they are given by the infinite n cohomology and model out the image of I star. So that means you impose some trace identities to the infinite n cohomologies, and then you get some finite n cohomology. So from this method, we get a bunch of cohomologies at finite n, but then there's a natural question to ask is that, are there any other cohomology classes than the cohomology class coming from infinite n? So in other words, the question is, if we consider finite n cohomology and model the image of pi star, and whether this equals 0. And in other words, by the exactness of this sequence, that means whether the image of this delta map is 0. In 2013, Xing and I, we tried very hard to find other cohomology classes that are not coming from infinite n, but failed. So we conjecture that all cohomology classes are coming from the cyclic cohomology. And more precisely, our conjecture is that this pi star map is surjective. In other words, this delta, image of delta is 0. We later realized that we were not the first one to propose this conjecture. Actually, in the book of Lode, this cyclic homology group, there is a similar conjecture. It's actually a stronger conjecture. It states that the finite n cohomology is still given by product of the cyclic cohomology, but with some constraint on the degree. So Lode's original conjecture has a quite obvious error, actually by a simple counterexample of this A with two bosonic variables without fermionic variable. And in this case, you can see that this map psi cannot be an isomorphism. But later on, Feijin fixed this error by proposing a corrected conjecture. And that conjecture actually agreed with Xing and I's the conjecture by Xing and me. So that's the pi star is surjective. And however, even with this correction, this conjecture contradicts with the existence of supersymmetric black holes in ADS5 times S5. So that comes about. So we can actually try to estimate how many cohomology classes we have from the, if this conjecture is true, then how many cohomology classes we have. So the estimation is to compute the dimension of the product of the cyclic homology. And we want to study a larger n limit and consider the homology degree, the small n scale like n squared. And in this case, we can estimate how many cohomology classes we have. That goes like e to the small n to the 5/6. And then if small n scale like capital N squared, that is e to the capital N to the 5/3. However, this scaling is much smaller than the thing we expect from the bulk dual black hole. So the number of black hole microstates that scale like e to the s, the entropy, and we also know that entropy scale like n squared. And we see that this e to the n squared is much larger than e to the n to the 5/3. So that means there must exist some other cohomology classes. And actually, these extra cohomology classes, if you consider this larger limit, you have much more these extra cohomology classes than the ones coming from infinite n. And we call these cohomology classes fortuitous classes. So basically, that's the definition. The fortuitous classes are the cohomology classes that given by after quotient out the image of pi, or equivalently that's in the image of delta. Okay, and this prediction from black hole is confirmed by the computation of the superconformal index. Basically, that's the Euler characteristic of the Q-cohomology. So the Euler characteristic gives us the number of bosonic cohomology classes minus number of fermionic cohomology classes. So it will give us a lower bound of how many cohomology classes we have. So more precisely, it's given by this trace. That is a trace over the space of operator. And so this J and the Q are the angular momenta that I introduced previously. In the Engels-Force-Williams framework, they are basically linear combinations of the power of the formal variable z and theta, and also the cohomology degree n. And so in a larger limit, this index has been evaluated, and the result is given by this formula. And you can see that it's scaled like n squared. So that really tells us that the number of black hole microstates is lower bound by something times n squared. And this is a quite famous result, and this result received the Frontier of Science Award this year. So from this computation, we know that there must exist. I mean, we are very sure that there must exist some other cohomology classes. And then the question is, can we really construct even one of them? So can we construct an explicit example of a fortuitous class? And so in 2022, by some very hard brute force search, we found the first fortuitous cohomology classes. That is, we work in the GL2 case, the simplest case, but we need to consider a very high degree. And so in total, we constructed explicitly around the 10 to the 5 cohomology classes, and only one of them is fortuitous. And after our work, later on, people found a very simple representative for this cohomology class, and is in this form. And you can see that this form looks different from the form that we previously have for the cyclic homology, cyclic cohomology. So in this form, for every side in the trace, there's only one derivative on this side, but this one is different. So for example, this one we have multiple derivatives on a single side inside the trace. But I mean, it's actually quite hard to see. I mean, because we need to also module exact module Q exact terms. So it's not that simple to see that this one is not the one that in the image of pi star. But we can, I mean, by some real computation, we can really see that this one is not in the image of pi star. And after our work, people have found several infinite towers of fortuitous classes in the GL2 and GL3 cases. And also using these infinite towers of cohomology classes, we can learn a new thing about black holes by playing with these cohomology classes. And so let me just, because of short time, let me just give two examples very briefly. So one thing we can play with these fortuitous classes is that we consider fusion rules of the fortuitous class with the graviton class or the cyclic homology class. And the fusion rule of them can actually predict new black hole solutions. And these black hole solutions are called gray galaxy and the dual dress black hole. So these black hole solutions are previously unknown and predicted by the fusion of these fortuitous classes and then later being constructed, really constructed. And another thing that this fortuitous class can tell us is that we can study the distribution of these fortuitous classes. So we can consider the space of this angular momenta. We have 5 angular momenta. And we can consider how the fortuitous classes distribute in this 5-dimensional space. And this distribution can actually provide us a very natural explanation of a previously mysterious charge constraint on the BPS black hole in ADS5. People have solved this. People have this BPS black hole solution for almost 20 years, and for the solution that people found, they all satisfy a very mysterious charge constraint. But the distribution of fortuitous classes can give some very natural explanation of that charge constraint. Okay, so for the remaining of the time, let me talk about the generalization to other theories. So recall that our framework, the algebraic structures. So first we need a nilpotent supercharge, Q and Q squared equals 0. And we also need that the space of operators sit inside this short exact sequence. So we have the space of operator at infinite n and the space of operator at finite n. And finite n is given by quotient of the infinite n space by some relation. And then we require the compatibility between these two structures. So we want this I and Q commute and pi and Q also commute. And if we have this, then we can write down this long exact sequence. And then we can define then we can define some cohomology classes. We call them monotone. They are the classes live inside the image of this pi star. And another cohomology classes, we call them fortuitous. And they are given by after we remove the monotone cohomology classes, basically by quotient out the image of pi star. And this is basically just very simple framework that we have. And this framework can be applied to many theories. So many theories has these algebraic structures. And then we can try to classify their cohomology in these two classes. So for example, we can generalize the 4D n equals 4 to 4D n equals 1 as CFTs. And in these studies, the Q-cohomology in this case, that gives us generalization of the algebra cohomology. And we can also consider the supersymmetric SYK model. And the Q-cohomologies are generalization of the causal cohomology. And we can also consider other theories, for example, D1, D5 CFT, ABGM theory, vector models, or like quiver or matrix quantum mechanics. And these theories will give us many new cohomologies, and most of them are unknown before. So let me also briefly discuss the bulk duo of these cohomology classes. So I will not explain them, but I will just state these conjectures. So there's one conjecture I propose with my collaborator, that is the monotone cohomology classes. So those classes are, in n equals 4, super Yang-Mills are the product of cyclic cohomology classes. And our proposal is that the bulk duo of them are microstates of the horizonless geometries in the bulk. And on the other hand, for the fortuitous cohomology classes, and the proposal is that they are microstates of black holes. And there are some other conjecture by another group of people. So they propose that these fortuitous cohomology classes, or the fortuitous states, they are strongly chaotic. But for the monotone cohomology classes or monotone states, they are at most weakly chaotic. Okay. But I do not have time to give further explanation of why we want to propose this conjecture. So conclusion, we have studied the supercharged Q cohomologies in n equals 4 super Yang-Mills, and black holes have provide a lot of insight into this cohomology. And the study of fortuitous classes also teach us a lot about black holes. And we expect this two-way exchange to keep deepening. Okay, thank you.